This is the Periodic Motion Homework Booklet, question number 7. A simple pendulum is given a small displacement from its equilibrium position and performs simple harmonic motion. You are asked to state what is meant by simple harmonic motion. That phrase is really expecting you to reproduce a definition for simple harmonic motion. This always involves two parts. If you look on the data sheet, you will find this equation, which is really the definition in a summary form, and you need to convert that into words. So you can see from the equation that the acceleration is proportional to the displacement. The second point is indicated by the minus sign in the equation. This tells us that the acceleration acts in the opposite direction to the displacement. Next, you're asked to calculate the frequency of oscillations of a pendulum of a given length. On the data sheet, you can find the expression for the time period for a pendulum. The question is asking you, however, for frequency. So you also need to use the fact that the frequency is a reciprocal of the time period. So here we have taken the reciprocal of the previous equation. Finally, you need to substitute the values into the equation, and be careful, we had 984 millimetres, so you have a power of 10 of 10 to the minus 3. That leads us to an answer of 0.5025 Hertz. However, there is a mark allocated here for using an appropriate number of significant figures. Looking back at the question, the only piece of data given was the length of the pendulum. This was to 3 significant figures, so we match this in our answer. Next, you're asked to calculate the acceleration of the pendulum for a given displacement. The standard equation, as found on the datasheet for acceleration in simple harmonic motion, is acceleration equals minus omega squared x. Also given there, you have that omega is 2 pi f. So simply combining these two equations and substituting in the values leads us to an answer. It is good practice to keep extra significant figures in temporary answers that may be used later. So you can see how I have carried an extra significant figure progressing from part 1 to part 2 of the question. Also be careful, we have millimetres once again, so we are using times 10 to the minus 3. Once we've achieved our final answer, we simply need to consider the best way to express it, and 2 significant figures is appropriate since we had 2 significant figures in the length. Finally, part C, we have a simple pendulum of time period 1.9 seconds is set up alongside a second pendulum with a time period of 2 seconds. They're displaced in the same direction and released at the same time. You are asked to calculate the time interval until they next move in phase. And very importantly here, you are required to explain how you arrive at your answer. So only one of the 3 marks is allocated for your final answer here. So notice the technique used here. This question could well come up with different values, so it's the technique that is important. So consider when the pendulums are next in phase. This would imply that the shorter pendulum, that's the one with the shorter time period as well, would have completed 1 extra oscillation. This would bring the 2 pendulums back in phase once again. Then, if we consider the longer pendulum with a time period of 2 seconds as having completed an unknown number of oscillations that we call n, we can say that the time represented by the 2 seconds times this number of oscillations would equal the time taken by one more oscillation of the other pendulum of period 1.9 seconds. So this is the bit that takes a little bit of thought. One pendulum will have oscillated n times, the other pendulum will have oscillated one more time. So then it's a case of some careful algebra, and you can solve to find n is 19. Finally, you want to find the corresponding time. You can look at this in two ways, both of which will lead to the same answer. So either 19 oscillations of the longer pendulum, so that's 19 times 2 seconds, or 20 oscillations of the shorter pendulum, both leading to an answer of 38 seconds. One final point, you may not have structured your answer in exactly the same way as I have done. So an alternative way of accessing the 3 marks were 1 mark for recognising that it was 20 oscillations of the shorter pendulum or 19 of the longer one. A second mark for commenting that there was a difference of 1 oscillation between the two, or a phase difference of 2 pi, and finally the third mark for the answer of 38.